Okay, so yeah, this is going to be our week 4 tutorial sessions for this course of thermal physics. So I will share my screen first and then um, yeah. So I hope my screen is visible to you, and if there is any problem in the visibility of the screen, or let's say if I am not audible enough, then please unmute yourself and let me know, because otherwise I will not understand. Okay, so here let me go full screen. So first avoid the initial pictures because I'll come to them later when the question comes. So basically what this lecture's content is about, it is mainly on Brownian motion, right? Brownian motion of particles, and how they behave, what are the required relations, and the theory and experiments that proved Brownian motion, because Brownian motion, you know that is related to molecular kinetic theory. That means the motion of molecules, the collision between molecules, etc. Right? So yeah. So this is today's 16th February, and this is our week 4, and the topic is Brownian motion. Okay, so first, because this is the tutorial session, so we'll be solving problems mainly and not discuss the concept of Brownian motion in detail as in the class, because you already have the class lectures. But uh, please let me know if you have any conceptual problem in any of the questions that we are going to solve, and I'll try to discuss it out so that it is clear in that sense. Otherwise, I will not go into too much of physics details, but only I'll cover the required details which are required and related to the parts I'm going to discuss. Otherwise, you can follow the lecture content itself. So basically, let us start with the problems then. Right, so again we have 10 problems, and the interesting part is that this week's lecture assignments that you have been given, most of them are, I think all of them, or actually most of them are similar to what I am going to discuss today in today's class. So basically, after I solve this for you, you will be able to fully solve that assignment all by yourself, or maybe because most of the questions may be similar as far I have seen, so that will also be helpful. So let us start then, right? Now let us start with the first question. So it is saying that an experiment with colloidal particles suspended in a liquid at temperature 30 degrees centigrade shows that the mean square displacement per unit time to be 1.5 centimeter square per second. Find the radius of a suspended particle where the Avogadro number Na is mentioned, that the standard number, and eta, that is the viscosity of the liquid that they are talking about. That viscosity is mentioned in the unit of poise, which is a CGS unit of viscosity, you know. So first of all, we have to again understand that what are the known quantities to you in this problem, and what is the quantity that you need to solve out of using these known quantities, and then you will know that exactly what relation or what formula mathematically you need to use to solve this problem, right? So basically first we have the information about temperature, because temperature is mentioned, 30 degrees centigrade, T is mentioned. Now mean square displacement per unit time is mentioned. So mean square displacement, you know already from the lecture, that if mean square displacement, if you signify like write it by this term delta x squared and then mean of that. So this delta x is basically the displacement, and squared displacement means delta x squared, and then the average sign over it, that is, this is the line on top, this means the mean or the average value. So this basically means our mean square displacement, and it is also saying that it is per unit time, because there is also per second in the unit. So basically this is divided by tau, that is the time of the collisions between the molecules, that this is displacement mean divided by this time unit is basically given you as units of centimeter square per second, and value is given to you. Now, Avogadro number is mentioned, liquid viscosity is mentioned. So, you have to calculate what is the radius r of the suspended particle. So, let me choose a blank page again and start to solve this. Okay, so this is basically because in this problem we have colloidal particles suspended in a liquid. Okay, so the system that you need to deal with is colloidal suspended suspended in a liquid. So you know that this kind of a system obviously will show Brownian motion. So it will show Brownian motion. Why Brownian motion? Because if this is your container of where the liquid is placed, so this is, let's say, the liquid, and in this liquid there are some particles, colloidal particles, which are suspended in this liquid. Let's say these particles are these blue ones that I am drawing here, and around these particles they are suspended into a background liquid, which is the medium in which it is suspended into. So basically in total this colloidal particle suspended in this medium is forming an emulsion, which is important to see actually Brownian motions, because these white dots are basically the molecules of the surrounding liquid medium, right? So this is your surrounding liquid medium, and the dots are like molecules of that liquid, and this blue ones are the colloidal particle that are suspended in that liquid medium. Okay, so naturally Brownian motion will be observed because these colloidal particles are also not very big in size, so they are also small sized objects that are only seen under microscope maybe, and so these surrounding molecules of the liquid will randomly and continuously produce or apply force from all possible directions on these colloidal molecules or colloidal particles that are suspended into it. So basically because of that impact from different directions of the surrounding molecules, so basically it is a molecular collision and motion sort of thing. Now these colloidal particles will have a continuous and random and irregular sort of a motion, which is basically a Brownian motion, right? And because it will have Brownian motion, so if you observe that colloidal particle under a powerful microscope, so then you will see that it will have some kind of a zigzag motion, which is happening because of the impact it is getting from all the surrounding molecules colliding and causing applying force on top on that. So because of which it can move in a random zigzag sort of a motion like this. Let's say I am trying to draw. So this is basically, let's say if you are observing that molecule and you are observing it in a microscope, and you are basically tracing out the trajectory that a particular colloidal particle, let's say we choose a particular colloidal particle, which is this one, let's say. Okay, let's say this is one. This colloidal particle we observe under microscope and observe its trajectory over a certain interval of time. Let's say like in the experiments for the first time when it was discovered, they took 30 seconds interval. So let's say we are tracing out what is the position of that colloidal particle after each 30 seconds. So that is how you trace out the trajectory of that molecule, and it will be just a random zigzag sort of motion. There is no particular directional preference or no like previously known idea of what the motion should be. It is just a random zigzag and continuous motion, which is important that it never stops. And if you now mark the trajectory, like if it starts from here, let's say this is at t equal to 0, and this goes from here to here, then after a same interval this goes to here, and then it goes here, and similarly it continues, right? After each similar time interval it will continuously continue, and let's say this is at time t. When you see, then it is here, so it is from where it has started and it is where it has reached after time t, and you have measured the trajectory after similar interval of time, uniform interval. Let's say this is the interval that you are taking your data in. Okay, after each tau interval you are measuring how much it is getting displaced. So because here we are going to talk about something called mean square displacement. So the idea to about the mean square displacement is important. So it is very simple that let's say if you consider there is a reference position where you start with, okay, so that is basically your, let's say this is your x naught position, which is initially let's say 0, okay, or x naught can be any finite value also. Now you start from here by your colloidal particle, and then after tau interval you see that the particle has moved up to this position. So this is in tau interval, okay, and you see this is the initial position, this is the final position, this is let's say I, and this is F, final position. So here it has let's say traveled a distance of to a coordinate of x1. So for simplicity we are only talking about a single coordinate or one dimension, x direction in this case, but in reality it can be there can be other directions involved also, but to make life simpler we are only going to discuss about a single one dimension motion as if. Okay, so this is in the x direction that you are going to measure how much it has displaced from its reference position. So this amount of displacement is basically your displacement along x direction after tau time interval. So this is your delta x, right? Now for the first time when it has done the motion, so then we call it delta x1. Now let's say it has moved to let's say from here to here in the next tau interval of time, okay. So basically it is next tau interval means after from the initial time t equal to 0, it has now passed 2 tau amount of time after this position. So it has now reached here. So what is your displacement then in the next in this next step? So here the displacement is, let's say now the x position of this coordinate position is let's say some x2 times some y2 value, which you are not mentioning here. But here let's say the x position has changed to x2. Now so its displacement between this point and this point will be this amount, which is basically your delta x2, which is your x2 minus x1, right? And similarly your delta x1 used to be x1 minus x0, and thus the process will continue if you now move on to another position, let's say here, okay, in the next time interval of tau. So here up to this you cover a time of 3 tau from your initial starting point. So what will happen is that here your next position will be at x3, right? So now from here x2 to x3 your actual displacement along x direction will be delta x3, let's say, which is just x3 minus x2. And because Brownian motion is a continuous motion, it never stops, right? So it will continue to have such kind of a zigzag random jittery motion, and many such displacements you will find. So all these displacements, because there are statistically you have to deal with it, right? So statistically speaking, so here you have to take some mean value or the average value over all of these quantities. So let's say you have all such displacements that you measure or observe by your observation on the particle, on the colloidal particle by your microscope, and you take the data for a significant long amount of time in a certain particular interval tau. Tau is the interval in which you take the data, or you basically measure the coordinate position of the particular particle at that position. So after let's say a significant amount of time, you have many such displacement measures like delta x1, delta x2, delta x3, many, right? And these are in interval time of tau, 2 tau, 3 tau, etc. And you go up to a long time, because then only your averaging will make sense. You have to take a large number of data for a particular statistical average. So then your mean square displacement, so you can think of it like a fluctuation as if. So this is not a significant deviation that you will observe, but from a reference position there is always a deviation, and these deviations you call it a fluctuation. So these fluctuations are denoted by this delta x sort of thing, which is the fluctuation in x direction, of course. These are called fluctuations, and here we basically are taking first a squared of these deviations. Like let's say you are taking first delta x, which is your deviation on first place, deviation of the particle from a reference position. And then you, because it is a square displacement, so the second term that comes after displacement is basically the deviation part. So deviation with respect to a reference position x0 with respect to some starting position x naught, let's say. So this displacement is your delta x. Now you have taken a term like squared. So you are taking a squared displacement, that is delta x squared, right? And then finally you have this term called mean or average. So basically you average over many such squared deviations or displacements. So that means you are basically taking here up to here, you are taking, like you have delta x, that means you will be taking delta x1, delta x2, etc. Then in the next step for square displacements, you have simply delta x1 squared, delta x2 squared, dot 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 similarly. And when you are taking an average of that, so basically you are saying that you are doing an average of this. Let's say for your simplicity, I am choosing to say there are n such data points that you have collected. So basically you will have delta x1 squared plus delta x2 squared plus delta x3 squared dot dot dot, and up to n number of times you have taken, so it finishes on n, so delta x n whole squared. So because you have taken the data n times, you have such n deviation data with you, so it will be averaged by the number n also. So this is the total number of data points taken, and now you average out all of them to calculate your mean square deviations. So this is a very important quantity in the Brownian motion problem, because it deals with the particle's trajectory or particle's position coordinate, that it changes with time. It observes it with a significant amount of time in a certain particular time interval, which is fixed and uniform for all. And then after that it measures the mean square deviation to understand how much fluctuation this Brownian motion property of the molecule has caused to the particle, and it actually relates by a formula with the viscosity of the liquid medium that the colloidal particle is suspended in, and also it has relations to the radius of the particle, that is actually something that you have been asked to calculate in this problem. So I will directly now write down the formula. That is a famous formula called also Einstein's formula for Brownian motion. And basically this is the heart of the Brownian motion concept. So by knowing this formula, you will be able to solve most of the problems. And by knowing this formula, you can actually around this formula, basically I would say that you can understand the whole theory and also the experimental approach of this Brownian motion problem. So mark this formula is very much important. So this is delta x squared, then the average of this is equal to RT by Na into 1 by 3 pi eta r into tau. So this is a very important formula. This is called Einstein's formula of Brownian motion. So for the first time in probably 1905, Einstein came up with this theory of that molecules do have a motion, and that Brownian motion can be a particular kind of motion that the molecules can have, and this is the formula he derived using the kinetic theory that is known for gases. So this Brownian motion is a motion that can be seen for all kind of fluid particles, like also gaseous particles and as well as liquid particles. Just you have to produce an emulsion, or that is basically you suspend some particle in some another liquid medium, fluid medium. So that is the concept, and later on it was also experimentally verified by the person called Perrin and some other persons also, that you will be we will be mentioning about these experiments in the upcoming questions also. So basically another person apart from Einstein also came up with this formula by a separate kind of derivation, but basically it is famous mainly in the name of Einstein, so we'll call it Einstein's formula only. Now try to identify the different terms that are present in this formula. First of all, this is known to us is the mean square deviation, statistically calculated over a long period of time. This R is, this is the universal gas constant. Okay, universal gas constant. This is valid for ideal gas when PV equal to RT is the ideal gas equation for 1 mole of ideal gas. So this I need not discuss more about this. Na is basically your Avogadro's number. Avogadro number is basically the number of molecules that are present in 1 mole of the sample. So this is the Avogadro number Na, which is value you know standardly known as 6.023 × 10 to the power 23. T is the absolute temperature in Kelvin, of the system, basically the colloidal particle that is suspended in the media, or any system that is giving you Brownian motion. So let us call it a system. Okay. And 3 pi, so this is constant. Eta is basically the viscosity. Viscosity, you know, this is a property of liquid which is basically acts like a resistance of liquid. So this basically like you have friction as a resistance, so you can think of it equivalent to friction of the liquid medium. So it basically obstructs the motion in of a particle in a liquid medium. That is how it works, and there are certain laws, Stokes law, etc. for relating to viscosity. But this is the viscosity of the liquid, or let's say it can even be a gas medium, so liquid, or I would say fluid medium, in which colloidal particle is suspended in, or in which colloidal particle is showing a Brownian motion. Okay, right. And this R is interesting because R is something that we have to calculate out of this problem number 1. So R is the radius of the colloidal particle in the suspension. So by choosing R, by default it means that we have chosen our colloidal particles to be spherical in shape, which has a radius of R. Okay. So this is a spherical shape we have assumed, and also we have assumed that all the colloidal particles are uniform in shape and size. So all of them has a uniform radius R defined to them. Okay. Uniformly spherical shaped particles. Okay. And tau is basically the time interval, which is also uniformly chosen. That means you cannot change tau continuously throughout your observation. You have to keep it at a fixed tau. If it is 30 seconds, then after each 30 seconds you have to take the data. You cannot measure one 30 second and another after 50 seconds or so. It has to be uniform. So this is the time interval between capturing the position to track the particles trajectory in the medium. Right. So now we have everything that you need to have to solve the problem. So also sometimes I mentioned that this R by Na that is mentioned in the problem, sometimes we also write it down as Boltzmann constant directly. Okay, so this is also known formula to you. You know that Kb times Na is basically your universal gas constant. So R by Na will give you Kb, which is a Boltzmann constant, and which has a value of 1.38 into 10 to the power minus 23 joule per Kelvin, or if it is in CGS, then it is 1.38 into 10 to the power of minus 16 per Kelvin. Okay. And this universal gas constant R value is 8.314 in SI units. And there are other units also, but I will not go into that right now. You can check that from internet. So now to solve the problem, first of all we have the information about temperature. So T equal to 30 degrees centigrade means 30 plus 273 Kelvin, which is basically your 303 Kelvin, right? And your this quantity delta x squared mean divided by tau, this quantity is also mentioned as 1.5 centimeter squared per second. Okay, so obviously this is centimeter squared, means this is the mean square deviation unit, right? And tau is the second time unit that is divided by in this term. And you have also information about the viscosity of the liquid, which is eta. Eta is basically 0.01 poise in this case. So here to know about the units is important, because otherwise you have to match the units to get a particular correct answer. Like if you are following CGS units, then we will follow CGS unit for all of the quantities. It has to be uniform. So 0.01 poise, here poise is the CGS unit of viscosity. Whereas the SI unit of viscosity is Pascal times second. Pascal is basically the unit of pressure, SI unit, and pressure times pressure into time is basically your viscosity, and SI unit is Pascal times second. And there is a relation between the CGS and SI unit, is that 1 poise is equal to 0.1 Pascal second. This is a conversion, right? So now let us choose to use CGS unit for this problem, because we will be getting the answer after ultimately the radius we have to calculate, right? So we will be getting the answer in centimeter. So if we want the answer in centimeter, we will be following CGS unit in all of them. So what we will do is that we now use this formula, delta x squared equal to R by N, you call it by Kb, which is the Boltzmann constant, and T you know from the equation, and rest of the terms are also there. So let us, then R is equal to, if you rearrange the terms properly, then R is equal to simply RT, capital RT by Na into 3 pi eta, tau was up, then delta x squared, right? So this is nothing but your RT by Na into 1 by 3 pi eta into 1 by delta x square average by tau, right? Now you directly put down all the information you have. Like you can either separately calculate R by Na by putting the CGS value of R, and the value of Na is universally known as 6.023 into, also mentioned in the question, the value of Avogadro number Na. Or because you already know that is R by Na is equal to Kb, you can directly use the value of Kb here. So let's say I directly use Kb. Okay, so Kb is because we are choosing to do in CGS unit, so everything in CGS, remember that. So CGS unit Kb value is just 1.38 into 10 to the power of minus 16 arc per Kelvin, into temperature in Kelvin unit came as 303 Kelvin, into 1 by 3 pi eta. Eta is also in CGS unit, so no problem, directly use that, 0.01 poise, into 1 by this thing was 1.5 centimeter square per second. So sorry, 1.5 into what was that? Yeah, 1.5 centimeter square per second. So now if you calculate it, you will get your answer. Probably I am not missing any other terms. So let me just calculate it once, because I am not also. 1.38 into 10 to the power minus 16 to 303. I hope you are also doing the calculation side by side. 3 into pi into 0.01 into 1.5. So we are getting 2.95 10 to the power minus 13. 2.95 into 10 to the power minus 13, and remember we are doing in CGS, so this is basically centimeter. Now you can also write it down as 0.29 into 10 to the power of minus 12 centimeter, which is your value of radius R. So this is your final answer, that this is in centimeter, this is the radius of the colloidal particle. So we have obtained the answer. Let us choose from the options. So you can see the correct answer is also marked here, that this is A, and this is also the accepted answer. So this is right. Now question number 2. It says that the horizontal displacements of a given particle in water for 11 successive intervals, each of 30-second duration, where these values are given for 11 times they have measured the like displacements delta x. This is in centimeter unit, again is CGS, and the tau, that is a uniform interval between those measurements, is 30 second. Okay, and here the total number of such intervals or such data points taken is capital N is equal to 11 here, and all of the delta x1, delta x2, x up to delta x11, these values are given in the bracket over here. Okay, and the temperature T is also mentioned as 18 degrees centigrade. You can convert it into Kelvin. Viscosity of water at that temperature, because it is temperature dependent quantity, is also mentioned in CGS, that is a Poise unit. So if the Avogadro number, that is one, that value is also given to be taken as Na, 6.0 10 to the power 23, then calculate the radius of the particle. So you can see that this problem is not exactly, but almost similar as the earlier problem, because the formula that you need to use is exactly same, because again you have the same set of information and the same quantity that you need to calculate out of that. So you need to again calculate what is the radius r of the particle. Only thing that is different from the previous problem is that here they had already mentioned to you what is the mean squared displacement per unit time directly, but here you need to calculate that from the data that is given to you. So this is basically, yeah, so we'll be, let's say, solving this question number 2. So basically they are saying that there are 11 successive intervals in which data of displacements is taken. So here n equal to 11, and the data that is present showing to you, so basically you have to remember the quantities like 0, 0, 5.6. So I'll prefer to calculate it first over here, because otherwise it is very inconvenient to go down there and then correcting all 11 values one by one. So basically we'll do it by the side, so we can directly check the values. So here let's say your delta x1, the first interval data is displacement is 0, then delta x2 is 5.6, then delta x3. Just follow the values as per sequence that is mentioned in the bracket on the question. So this is 4.7. So basically it is meaning that it is moving to the negative x direction now. Okay, so let's say we can pictorially draw it. Let's say this is our initial position, and after tau interval it has not moved because the displacement is 0. Then after this it has moved in the positive x-axis by a value of 5.6 into 10 to the power minus 4 centimeter is also there. So into 10 to the power minus 4 centimeter. Okay, so this is the second position, and then in the third position it goes to a position, let's say here, where it has been moving to the negative x direction. So in the 3 part, in the x2 to x3, the movement is delta x3 is negative because it is going in the negative x direction now, and similarly it follows a zigzag continuous motion. So I am not writing down all of them separately, but you can follow that up to delta x11, the last value is 16, right? Yes, as per the problem. So this is 16 into 10 to the power minus 4 centimeter. So all of these has 10 to the power minus 4 centimeter alongside. Now how to calculate the mean square deviation here? So I have already shown you the formula for that. So this is basically mean square deviation is basically all of the different data of deviation statistically taken, like delta x1 it's squared, then delta x2 it's squared, and similarly all of the data you have, you take a square for that, and then you divide it to average it out by the total number of data, that is 11 in this case. Okay. So basically you have to have 0 squared plus then 5.6 into 10 to the power minus 4 squared plus minus 4.7 into 10 to the power minus 4 squared plus dot dot dot, it continues up to the final value 60 into 10 to the power minus 4 squared divided by 11. So simply choosing, so you take it common as 10 to the power minus 4 squared is 10 to the power minus 8, and then all of the terms like 0 squared plus 5.6 squared plus this minus terms will be plus in the squared, so 4.7 squared plus dot 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 16 squared divided by 11. So if you do that, if you do the maths, then you will get a value of mean square displacement as 1.18 into 10 to the power of minus 6 centimeter squared. Why centimeter square is the unit? Because this is just delta x squared mean. This is x squared, right? So there will be a centimeter square unit. And you have calculated it from the data that is given to you in the question number 2. Now once you have this information, you can directly now use the same formula that you used for this equation for this question, and you will get the R value. So for the final answer, let us solve that much, that your R is simply your kBt tau by 3 pi eta delta x squared average. Now because we are choosing to do in CGS again, so kb is 1.38 into 10 to the power minus 16 into the temperature is basically, I think it was 18 degrees centigrade, right? So temperature equal to 18 plus 273, it is 291 Kelvin. So this is 291 into tau, that is the interval time, is basically 30 second. So this is 30 second divided by 3 pi into eta. Eta was mentioned in the question as 0.1 poise, right? So this is also directly in CGS unit, so use that directly, 0.1 into this mean square deviation is basically, you calculated it as 1.18 into 10 to the power of minus 6, right? Yeah. So now once you have all of them, you calculate it by using your calculator, and I have already calculated it, so the answer I know is coming as 1.08 into 10 to the power of minus 6 centimeter. So this is most likely chosen as your option number C. So let us go back and choose the correct option. Yeah, so the correct option is 1.08, which is your option number C, correct answer. Now question number 3 is that in his experiment on water suspension of gambos or at 20 degrees centigrade, Perrin observed an average of 49 particles per unit area in a layer at one level and 14 particles per unit area at a level that is 60 microns higher from the earlier level. Then calculate what is the effective mass for each particle, where the Avogadro number n is given and the gravitational constant, which is the universal constant again, g value is also given. So right, so here now this problem is a bit different from the earlier two problems that we have just now solved, but the problem is again based on Brownian motion itself. So here we will deal with, so this is based on the famous experiment by Perrin. Perrin is who first experimentally verified the theories mainly solved by Einstein and others, who came up with the molecular kinetic theory and molecular motion, which is called Brownian motion. So Perrin's experiment, he is taking the he has taken a water suspension of gum. Basically, this is the colloidal media that he has used as a to form an emulsion, and he has suspended it into water, and the temperature is mentioned as 20 degrees centigrade. Then average number of particles per unit area is 49 at one level, and there is another level of that liquid suspension is basically which is 60 microns above that level, and there also number of particles per unit area is given. So then what is the effective mass of each particle? So first of all, to solve this problem, I'd like to, before mentioning the formula that you need to exactly solve this, I would like to give you the picture for this problem, because ultimately this will be helpful in also solving some other parts of the similar problem that you will face in the upcoming questions. So this basically deals with the vertical distribution of Brownian particles. Like if you consider a column of vertical particles, Brownian particles, which are like Brownian motion, Brownian particles or Brownian particles in a medium, which are forming a layer by layer formation. like say you have a suspension only, so there are separate layers in separate heights in that suspension, and if you think of it as a total column of liquid and that colloidal particles, so how the pressure at the different layers and how the molecular number density at different layers are connected, what relation do they follow, is basically what we are going to derive now. So this is the particle distribution of Brownian particles. So we are considering a gas of Brownian particles, that means particles that follow Brownian motion concept, or that prominently can show Brownian motion. Gas of Brownian particles in equilibrium at a constant uniform temperature T and under gravitational force field, which is given by G here. Basically it means the gravitational acceleration. So under this gravitational field, the Brownian motion is present as a system, and we consider the system is isothermal. That means everywhere the temperature is uniform, and that is T here, let's say. Okay. And we are only going to deal with the vertical column of the gas. So take okay. And by vertical I choose to say z cap direction or z direction. So let us draw a diagram here. This is, let's see, your base level. This is one layer, and this is another layer at some certain height. So this is your base level or reference level, let's say. So this is acting as your reference level, and this is at z0. Okay, because we are only talking about vertical direction, so the vertical position for the base level is, let's say initial position is z0, and here the pressure of that all the molecules present here is p0. Then at a certain height from this base level, which is, let's say, a height of z, here the pressure of the Brownian gas molecules is p, and another level, so this is level 1, let's say, this is level 2, let's say, this is the base level over here. So another level is level 1 to level 2 is just dz. Okay, now and here the pressure is also higher, p plus dp. So basically you have a liquid column like fluid column like this, or it can also be a gas column because we are talking about gases. So this dotted area I am discussing here is a column of gas with Brownian particles, or column of Brownian gas. Here the height or thickness of the column is dz, because here it is z, and at level 2 the height is from the base level, obviously calculated from the base level, is z plus dz. So the thickness or the portion for the column between these two positions is just dz only. Okay, and there is also this P and P plus dP. So the pressure of the gas that the Brownian molecules of gas do have is at height z it is P, and at height is z plus dz, the pressure is P plus dP. Okay, so P, let's say, and pressure of the gas molecules at height d plus dz is equal to slightly higher P plus dP, and the density that the column of gas here has is rho, which is the mass density, mass per volume. Now, what will be the net force for this column marked by the yellow dots over here? So, net force of this layer is P plus dP minus P into 1 plus Fg. Now, let us remember or let us discuss what are the different terms over here. Like, basically you are talking about, we will be, for our simplicity, we will be choosing gas layers such that all of them has unity cross section area. So, we choose all gas layers cross section area is equal to 1 unity. So you know that the force equal to just pressure into area, because pressure is force by area. So because here the area is unity, so this is just multiplied by 1, and the force gradient is basically the difference in force between the two layers of the liquid column. So that is at z and z plus dz, and the pressures are P and P plus dP. Okay, and Fg is the gravitational component on that same particle. So this is the gravitational part of force okay. Now what will be the gravitational force? Of course, because you know that this is basically m times g, that means the mass times the gravitational acceleration g. Okay, so for ideal gas, you know that this is obviously first m times g. Now for ideal gas, you know that Pv equal to RT, and if the density of gas is rho given, so that is basically m by v. Here we all write it down in terms of capital M and V, because I mean to say the molecular weight, or for 1 mole the weight is this capital M, and V is the total volume for that sample. So this is capital M by V. Okay, and V is basically, you can write it down from here, this is RT by P. So this is M by V is basically the density of the gas, is M by V is MP by RT. Okay, and the net force F net is equal to simply P plus dP minus P, so P and P cancelling out, plus Fg is MP by RT. Now because you are also saying that this gas layer column is at equilibrium, so the net force F net is equal to 0. So in that case your dP plus MP by RT equal to 0, or your
Hello, ma'am.
yes, I think, sorry, I missed some of the part, right? I missed the G part. That is what you are trying to say?
Yes.
Yeah, sorry, I missed the G part. So this is MP by RT into G. Also, sorry, yeah, let me check once again. I missed another part because I was talking about density only. So let me check again. So rho is the density, right? So we have to calculate the mass. So mass is equal to density times volume. So density you can calculate as this, and then for volume you have to take area into the thickness, or in this case the height difference in that column, right? So for this particular column the height is dz, and the area you are choosing as unity cross section area, so the area is taken as 1. So in this case the rho times the area will be 1, and the thickness or the height difference for that particular column is dz. So this is just rho dz is your mass in this case. Okay, and so basically your gravitational force on that layer is basically your m times g. M times g is your rho into g into dz. Now rho value you have calculated here, that is mp by rt. So this is mp by rt into g into dz. So I had missed some of the terms while doing this, sorry for that. So this is mp by rt into g into dz will also be there. So g to
Ma'am, one more
dz.
thing.
Yeah.
Now I want to know that why you are subtracting the P plus dP minus P.
Yeah, basically because you know that pressure is basically your force by area, right? So means pressure, that the quantity is there, is also connected to some kind of force. Now for this particular column, when we are considering between z and z plus dz, for that it has basically, you can think of it like two surfaces of the gas layer. This is one level and this is another level. So to get the net force on it you have to take the gradient of the pressure that is actually effectively acting on it. So we cannot take the entire pressure, right, because this is the column you have to deal with. So on the two surfaces the pressure values are p plus dp and p. So just like between z and z plus dz, simply saying you had to take the effective width as dz, right? So similarly the effective pressure will be also p plus dp minus p, which is basically dp. This is basically a mathematical way to do any kind of, like, you take elements like this whenever you have to choose you have to solve something. So you first, for simplicity, you choose an element like that. Let's say for spherical cross section you choose a like cross section, what do you say, area, annular portion with a radius of dr, right? Similarly here we have chosen a column of that gas that you are dealing with, which is between these two surface of heights z and z plus dz, you can think of. So their effective height is dz, and the effective pressure acting on it is basically a subtraction of both of them, so it is basically dp. And because you are wanting to convert the pressure into force, so, and the uniform cross section area is unity to make life simple, so because of this your force becomes p plus dp minus p into 1, which is basically dp. Is that clear?
So that two forces directed along the opposite side.
What? The forces?
The forces on two layer
Mm-hmm.
actually act on opposite side. Yeah.
Yeah, basically, so effectively you have to like take the pressure difference, of course. Otherwise, how do you get the net pressure here? Because your gravitational force will be pulling it downward. If I think of it like an entire object, so Fg is downward, and in the same direction, your this thing is in this direction, and then again this thing is this direction. So here, so I don't know what is the part of confusion that you are saying exactly, but you have to take a pressure gradient, right? Because this is not adding up. So there is some gradient that is acting in this case.
Okay, thank you.
Yeah. So that's dp. So let us continue with the derivation. So dp by p is basically your minus mg by rt dz. Okay, then so we have to take an integral to solve this. So we can take other constants outside, and for the integral limits you will choose pressure from the initial pressure p naught to a final pressure of p, and the initial value of z as z naught to a final level of height z, because you are choosing only the vertical direction. So it will be simply ln of, if you integrate, ln of p by p naught equal to minus mg by rt z minus z naught. So this p ln, yeah, so we can remove ln and directly take an exponential on the other side. So p by p naught is basically e to the power of minus mg by rt z minus z naught. Then p equal to just p naught e to the power minus mg z minus z naught by rt. Alright, so this is the final expression. This is also known as sometimes I think barometric equation it will be called, because this actually gives you how the, because this is also valid for gaseous particles, because they also show Brownian motion. So because in air this kind of a pressure equation that is maintained as per the height difference. So if you go from z naught height to z height and there is a gravitational force into action, and m is basically here the don't forget here m is the mass for 1 mole. Okay, so that's why I am using capital M, and because of this you have universal gas constant R, which is also valid for 1 mole. If the quantity is not 1 mole, then you have to convert it accordingly. And then pressure at initial position is P naught, which is your base level, and at certain height the pressure you can calculate using this expression as P. And you can see that there is an exponential decrease as you go towards higher Z value, so this difference will increase. So basically the total pressure as you go up and up, it will exponentially decrease, because it is e to the power minus, right? Now why I am solving this, because this will also be needed in another problem that will be going to solve next, but you can connect it directly with molecular number densities. Okay, because you know there is a formula called P equal to NKT, right? This P is the pressure, N is the number density, that means number of molecules per unit volume, and K is basically your Kb, which is the Boltzmann constant, and T is the absolute temperature. So you can see that your P has directly proportionality connection with N, and KBT both are constants. T is constant for a particular temperature. So this formula can be equivalently valid for N also, because other things are just constant, right? So because of which you can also write it down as your N equal to N naught e to the power of minus M G Z minus Z naught by RT. So this is molecular density, that means molecules per unit volume. Okay, and yeah, so now it is probably time. Also there is so let us go back to the question, and then I'll discuss the rest of the quantities that we will need. So this is question number 3. So we have to calculate now the information given to us is the temperature, okay, and the average of 49 particles per unit area. So number of particles per unit area in a layer is given. So in the formula we have the quantity as small n, which is the number of particles per unit volume, but here they have given you the particle number per unit area for one level, let's say at Z0, and another level after a distance, after a height of 60 micron, they have given that the number of particles per unit area is 14. Then the effective mass of each particle you have to calculate. So also I have to tell you the concept of effective mass over here. So now to match with this problem that is given to us, if you draw a diagram roughly, so this is your initial level or level 1 you can say, and this is your level 2. This is, let's say, at Z0. We can consider this as 0 level just for reference, and here the next level is Z. Okay, so and the distance or the vertical distance between these two levels is given to you, which is 60 microns. Okay, and also the number of particles per unit area. So here one thing is important, that we consider here that each of these levels are of uniform uniform width, as if, because there is no mention about any thickness or anything about each layer, right? So we can consider it to be just a single line of layer or like that to simplify things, and we can think of it like a equivalent number density, because it is in dimensional, so you can just directly convert it into other dimension, because there is no information about the thickness of each layer, so you can consider it is just a single line of layer, and so thickness value can be unity in this case. So we can directly say that what is the number of particles per unit area is basically the n, the number of particles per unit volume in this case. We can equivalently say that, and we choose choose from the question that is given to us that on the first level the number n0, let's say we say it n0, is given as 49, and on the level number 2 the value of n is given as 40. Okay, so basically the idea is, because there is no information given to us about the thickness of each level, so we just take it as unity to simplify things, and instead of saying number of particles per unit volume, we equivalently then say it as number of particles per unit area. So I hope this is clear first of all. And now we have that information that what is your Z minus Z0 in this case is given to you in the question as 60 micron, which is in SI unit is 16 to 10 to the power minus 6 meter. Then also you have to calculate what is the effective mass of each of the particle. So this is not simple mass, this is effective mass, so this is different. Let's say this is m in this case, and for such colloidal suspension of particles, the effective mass has a formula as if 4/3 pi r cube into d minus d prime, where this 4/3 pi, sorry, this 4/3 pi r cube is basically the volume part. So this means that you are by default considering your molecule to be spherical, and its volume is 4/3 pi r cube, radius is r, and d minus d prime. Why? Because you are taking an effective density, because you know that mass is basically volume times density, and instead of directly multiplying with a single d, which can be a density, d is your density of that particular molecule or the particle, then what is d prime? D prime is basically the density of the medium in which it is suspended into. So density of the surrounding medium of suspension, which is basically effective for causing Brownian motion. So because in Brownian motion physics you have a particle which is surrounded by many other small molecules of the surrounding media of that suspension, which is causing it to have Brownian motion. So you have to choose an effective density, which is basically a subtraction of both of the densities, d minus d prime. That is why we call it effective mass, because this is coming related to effective density. So this is the idea. And now we can directly go to using the formula we have just calculated before, which is n equal to
Yes.
m naught. Yeah, so you have something to ask?
Yes.
Yeah.
I want to know that why I should subtract here, why the effective density is there to calculate the effective mass.
Because the particle is not by itself in the medium, it is affected by, it is getting impacted by all the suspension medium's molecule on it, because they are giving it a net force from all possible direction, which is basically the physics of Brownian motion, right? So it is, when it is inside a medium, you have to also consider the effect of the medium on it. So that is why effective mass, because the particle is not a free particle. If let's say you are probably familiar with this idea of free electron, etc. So there also, when the electron is all by itself in a sample, in a medium, then you can say that its mass is free electron mass m naught. But whenever it has all other interaction terms present out all around it, so then because of those interactions, its mass gets modified, then we call it effective mass. So similar thing happens here, that the particle is actually getting affected, it or all the other molecules surrounding it is interacting with that particle, producing impact or force on that particle, because of which you have to take the effective density. You cannot deal with a single particle's density here.
So it is the effective mass of Brownian particle.
Yeah, so it is the mass of that particle that I I had drawn a diagram at the starting. Let me just, yeah. So this is what I had drawn roughly. So like say this is a liquid medium, or any, it can be a gaseous medium also. Basically it has to be a fluid suspension, right? So like for the famous the Brownian motion, the is named after Robert Brown, who observed it in the pollen grains, in the motion of pollen grains, where the pollen grains were suspended in water medium. So you can choose your liquid medium suspension here to be water. And the pollen grains are this blue particle here, blue balls, which are, let's say, your pollen grains. So I'm just naming them so that it is easier to identify. These are the colloidal particles that I am talking about, and this is suspended in the background of this water medium, suspended in water. So this is as a whole forming your system, which will show Brownian motion. So now when you take this sample under a powerful microscope, you will observe. So there are plenty of videos, of course, in YouTube. You can observe them. This is very fascinating. We'll see, they are demonstrating that if you take a sample like that and take it under a slide in and under a microscope, you'll see that over time these colloidal particles, because of the impact it gets from the surrounding water molecules, it moves in a zigzag sort of dancing sort of motion. It continuously moves, and that motion never stops, and you cannot see it in naked eye, but you can see it in under a microscope. And also there are some other factors, that if the particle size is too big, then it is you cannot see that motion even under microscope that much, because there is a direct connection with radius, right? You saw that the mean square displacement delta x square average, that has a inversely proportional relation with radius, right? So the larger is the radius of the particle, that means the larger is the particle that you are putting in the medium, the mean square displacement value even decreases. So you cannot see, even if that is present, that motion is present, but it will not be visible, because from all other directions the forces will be cancelled out, and effectively you will see no Brownian motion, because of which you do not see Brownian motion in everyday objects. You only can see Brownian motion in small particles under microscope because of this thing. So do you get my point? Basically there are two objects over here, so surrounding medium of that liquid, which has many molecules producing force on these blue objects, which are your colloidal particles, and the mass we are talking about in that formula below is the mass of these particles. So you can say this mass is capital M, or if it is 1 mole of equivalent mass, and it can be effective mass of small m in this case. So do you get my point, what I am trying to say?
Yes, but density is mass per volume. So in case of both the guest and host molecule, so what volume is considered? Actually, the volume of the solution.
uh, Density, for density.
Yes.
So the liquid medium has its own density as a container's volume you have to then take. but for the colloidal particles it will have a volume of its own. Like, because we are assigning a radius r to the particle, right? We are considering that this is a spherical kind of a particle which has a radius r. This is your colloidal particle which is like a sphere. Not, this is ideal assumption, and that sphere has a volume of 4/3 pi r cube, right? So that is what we are choosing as the volume of the colloidal particle. And the external fluid medium can have a volume of the container, of course. So is it clear now?
Yes.
Yeah.
Thank you.
So let us then move on. So our formula was n equal to n naught. So what was the formula? N equal to n naught e to the power minus mg z minus z naught by rt. So for our purpose, we call this capital M, because I said that this is molar mass for 1 mole. So if you now deal with mass for a single particle, then you have to multiply this small m by Na. So mass of each particle into Avogadro number, that means number of particles present in 1 mole amount. So this is giving you your capital M. So that we replace in the main formula. So you'll get e to the power minus Na into m into g z minus z naught by rt, right? So now your ln of n by n naught will be simply, so because there is a minus sign, so we prefer to write n naught by n so that the minus sign can be tackled directly. So n naught by n equal to then Na mg, this exponential becomes ln on the other side divided by rt, right? Then you can also say this Na by r, this term you can call it directly by kb, right? 1 by kb basically, because r is kb times Nm. So now look at what information you have in hand. So first let us separate out this m term. So m is basically your rt by Na into 1 by g z minus z naught ln of n naught by n. So now put down the value. So I'll directly write r by Na as kb. So kb has a value in SI unit 1.38 to the power minus 23 joule per Kelvin, and the temperature in our case is given as 20 degrees centigrade, which is 20 plus 273, it is 293 Kelvin. So the T is 293 divided by your G value is also given in the question. This is 9.8 SI, and Z minus Z naught is the height of the height difference between the layers, which is 16 to 10 to the power minus 6 meter. So everything in is SI here, and N naught by N is basically 49 by 14. So another thing you can do over here, if you have problems in assuming that the layer of each layer is of unity thickness, you can also say that it has a certain thickness of T, and because each layer will be of same thickness, so here basically it will cancel out, right? Because there is a ratio over here. So whatever is the thickness, it is same for both of the layers. So it does not matter whether you are taking number density, that means number per volume, or number per area. So ultimately in the ratio both will be the same if both the layers has the same thickness. Okay, so you can directly write down this n naught by n by this ratio of 49 by 40. Okay, basically because number per volume is equal to number by area into thickness T. So layer 1 n1 by layer 2 n2 is basically number of molecules in the layer, let's say it is capital N1, divided by the area of this layer into the thickness of this layer, and the number of molecules in the second layer is, let's say, this, and both the layers has the same thickness T. So then this information is given to us in the question, N1 by area and N2 by area. So we can easily separate it out. Let's say we call it N1 prime, divided by thickness that is not known to us from the problem, and this is N2 prime by thickness. So this thickness and thickness automatically cancels out. So basically whenever you are taking your number of molecules per unit volumes ratio, you are basically similarly, like the ratio is same for number of molecules per unit area also. So that is how we can directly use this or write this as 49 by 14 over here. And once you calculate this, you will get the value as 8.61 into 10 to the power of minus 18 kg. So this is your final answer. Let me now check the time once. So how much time we have left? Yeah, so we have still 45 minutes time left. So I hope. So this problem became a bit elaborate because I was deriving the whole thing. But after this, because we have done most of the derivation, so we can now directly use the concepts and the formula. We do not need to give time in derivations anymore. So just quickly choose the option. This will be option D. Now let us move on to question number 4. It is saying that observation on Brownian motion of a spherical particle of radius that is given, r is given, in water at 27 degrees centigrade. So T is mentioned. So and viscosity of that medium eta is also given. And see that all of them are in SI units. Okay. Now if the value of the mean square displacement in 2 seconds, that means you are taking the interval of taking the data tau as 2 seconds is given, and the mean square deviation is also given, that means your delta x squared average is given. Then compute the value of Avogadro's number. So you probably know already from the lecture that these Brownian motion problems were excellent experimental tools to actually directly calculate the Avogadro's number. Basically the parents experiment that was done at that time, he directly could calculate the Avogadro's number by his data logging and by his experiment, and at that time it came very much closer to that today known accurate value of the Avogadro number, which is 6.023 into 10 to the power 23. So he did a similar kind of thing. Here the problem is based on that you have been given information about the Brownian motion and you have been given all sorts of information that are there to know, and you have to calculate the Avogadro number backwards. So the formula is just same, just the concept is also the same. So we'll directly use the formula without going into too much detail. So question number 4 is basically directly using the formula, substituting all the values that are given in the information. So you remember that your mean square displacement has a formula like this: RT by NA, Einstein's equation, 3 pi eta r into tau. Now in the problem you have to now calculate NA. So you take the Avogadro number as the unknown value and rearrange all the other terms. Okay. Now you put down quickly what are the known values to you. So take everything in SI. So R is 8.314 joule per SI unit, and T is 300 Kelvin given in the question, because I think it was 27 degrees centigrade mentioned in the problem. So that if you can convert into Kelvin, so this is 273 plus 27 is 300 Kelvin. And your tau, which is the interval of taking the data, is given as 2 seconds divided by 3 pi into the viscosity value was given as 10 to the power of minus 3. This was in Newton second per meter square, which is basically the SI unit equivalent to Pascal second of viscosity. And then the displacement mean square is 0.4 into 10 to the power of minus, sorry, I think I am taking some other value, 3 pi eta. So just let me check what are the values once. Yeah, so 1.7 into 10 to the power minus 12 is delta x squared average, and viscosity is 10 to the power minus 3. Sorry, I was putting down the value of R. So this was the R value. Yeah, so this is the R value that I am writing down here. Eta value is this thing, and delta x squared is basically 1.78 10 to the power minus 12. So once you calculate it, you will get your answer as 7.4 into 10 to the power of 23 number per mole. So you can see that this problem is giving you Avogadro's number of 7.4 10 to the power minus 3 per mole, whereas the actual known accurate value of Na is, the order is same 10 to the power 23, but the initial value is 6.023. So this is a direct, like the calculation of how actually at that time the experiment was done to indirectly calculate the Avogadro's number and how close it can come to the, sometimes in the problem we can also be asked to calculate that, compare this calculated value with the actual known standard value of Avogadro's number. So basically then you have to take a ratio of them and see that how much that deviates from the actual value. But here that is not asked in the question, so we'll leave it here, and you can choose it from the options that probably it is coming in option number B here. Okay, option number B, and that is the correct option. Now problem number 5 is the horizontal displacements of a Brownian particle in a medium at temperature 20 degrees centigrade in 11 successive intervals of 30 seconds. So this is similar to the earlier problem that you have seen here. We had calculated the delta x squared average from there. So I think the values are just the same. So yeah, and all 11 displacement values are given. So all similar values. Now the additional thing that you have to calculate over here is the diffusion coefficient of that medium. So in the lecture you have been given the derivation and the formula for that. So I will not go into the detailed derivation here. I will directly use the formula and we will solve this. Okay. So let me solve it here only. So from the earlier sum, we have already calculated what is your delta x square average. What was it? It was 1.18 into 10 to the power minus, I think the unit is different. Yeah, the unit is different. So here the unit is micron. Okay, here the unit is micron. But in the last problem, the unit was given in 10 to the power of minus 4 centimeter. Basically, so you have to take care of that. So I have already calculated it. So you can calculate it by similar means and you will see that the value will come. Basically you have to choose this everything 0 squared plus then 5.6 squared dot 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 up to the last value, and because it's in micron, so you have to take into account 10 to the power minus 6 and then whole squared of that, and then average it out by dividing by 11. So do this carefully and you'll get 1.18 into 10 to the power of minus 10 meter square is your this value. So yeah, basically this was in centimeter square, so this is same. Anyway, so if this is your delta x squared, then the diffusion coefficient D can be defined from the formula as kt by 6 pi eta r. This is the formula that you will directly use. So also you know that delta x squared, this Einstein equation has a formula that this is kt, where k is a Boltzmann constant, of course, 3 pi eta r into tau. So you can substitute this part over here to get your D value. So from here your kt by 3 pi eta r is coming as delta x square average by tau. And this is just half of that, right? Because there is a sixth factor. So 1/2 into this term that we have just got. So this is half into, we substitute this by the known value, known information to us. So this is how we get D. Now delta x squared we have just calculated. So this is 1.18 into 10 to the power minus 10 divided by 2 into the mean interval of the time is given as 30 seconds. So if you do this, you will get 1.96 into 10 to the power of minus 12 and the unit will be meter squared per second. So this is your diffusion coefficient D for that particular problem, and let us mark the answer. So we have got 1.96, that means first option, right? Then question number 6 is that the pressure at sea level, so this is the exact problem that will utilize the whole derivation that I had just done for the earlier question. So but here we will directly use a barometric equation in terms of pressure. So let us read the question and you will understand. It is saying that the pressure at sea level, which is your base level or reference level in this case, at, so just one second, I have to connect the charger for the laptop. Just give me 1 second. Yeah, so the base level or sea level pressure is given as temperature is mentioned, so T is here, and the base level pressure, let's say call it P naught. P naught is given in Newton per meter square unit, value is given. Now at a certain height of the another layer, the pressure, let's say the pressure is P here, is 1 by 16 times the pressure at the sea level. That means here the pressure is P naught by 16, right? So then if the temperature is increased 4 times, then what is the pressure at that height? So first of all, let me now go to the blank page and start freshly. It's problem number 6. It's basically your T is 27 degrees centigrade. So this is 300 Kelvin. And let us draw a quick diagram for us to understand that this is your sea level. This is at Z0, which is let's say at 0. And this is your another level that you are talking about in the problem. And this is let's say at height Z. So this distance, this whole distance is the difference between the sea level and the another level, and we call this height as H. So H is Z minus Z0 here. Okay, we call this the height of the level from sea level. So the pressure at sea level is P naught, the value is given to you, and the pressure at another level, the value is said to be P naught by 16 times the earlier value, 1 by 16 times the earlier value. Now because you are dealing with air molecules obviously, so air you can also think of it like a suspension of many colloidal particles, because there are many other particles in air present and air is a gaseous medium, so it is kind of like a suspension. And whenever there is a suspension and a colloidal particles in a medium, you know that will show Brownian motion. So it will follow Brownian motion for this case, and the physics will just be the same as we derived for the barometric equation just above this part, that we had derived this equation, right? P equal to P naught e to the power minus mg z minus z naught by RT, where we had a diagram like this. So now the problem is exactly the same. Your base level is just the sea level, and the level you are asking, the question is asking you about is here. So you know that you have the distance, the height difference between the two levels, you know the pressure here, you know the pressure here, and now you have to utilize directly this formula to, I think what you need to solve is basically the pressure on the other level. So let us directly now use this. So P equal to P naught e to the power of minus mg z minus z naught by RT. So you have been given the information that P naught at that level is P at that level is basically P naught by 16. So P naught by 16 is equal to then P naught e to the power minus mg. Now because we have redefined this z minus z naught as the height of the level from sea level is as h, so we directly write it as mgh by RT. So this P naught and P naught cancelling out. So you have e to the power minus mgh by RT equal to 1 by 16. So you can rearrange the object so that now mgh by RT is equal to simply ln of 16, right? So then you have the information about mgh by RT. Now this is when the temperature is given as T. Now what will happen is the temperature is, as per the question, if the temperature is increased 4 times, that means now your temperature changing into 4 times T. So then what will be the value of change in this term. So all other terms will remain constant because mass will not change by temperature, gravitational constant will not change by, acceleration term will not change by temperature, height will be fixed, r is also universal constant, no change. Only the temperature term is what is going to change in this whole term. So this becomes now, instead of t, this becomes 4t. So the value will now become ln of 16 by 4 then, because there is an additional division by 4 now present. Okay, so now you can directly use the formula and get the value of P, which is the pressure at the level at a height h from the sea level. So you have P naught e to the power of minus mgh by r into 4t. Now P naught is something that is given to you in the question as 101,325 Newton per meter square unit. You put that value and then e to the power of minus this value is already you have calculated as ln 16 by 4. So either you can directly use your calculator to solve that, or you know how ln terms work, so you can simplify it also by yourself, that ln of 16 divided by 4 means 1/4 into ln 16, which is basically ln of 16 to the power of 1/4, right? So 16 to the power 1/4 is no, this is 2. So you have 101,325 e to the power of minus ln 2. So this e and ln will be compensating each other. So you have 101,325 into half, because there is a minus sign, so it will be like half. So you have the answer as 50662.5 Newton per meter square. This is your answer, and you can see that the pressure has been, by the change of temperature by 4 times, the pressure at that level has degraded half of that pressure from sea level. So this is the pressure at h height from sea level. So simply by using the Brownian motion idea, you can calculate how much the pressure will be from a certain level from sea height. So this is also matched with the solution. This is what we get. So the answer is C. Now question number 7 is that in which case the motion of the Brownian particles is greater. Now Brownian particles motion, so we can directly either take the concept of this formula that we have just used multiple times. It's RT by Na 1 by 3 pi eta r into tau. So here you will directly see that this mean square displacement is directly proportional to temperature T. This is inversely proportional to viscosity because it is 1 by eta. It is also inversely proportional to the radius because 1 by r. So what does it tell you is that as you increase the temperature T, it will be directly proportional, so the mean square displacement will increase. That means that Brownian motion has increased, because obviously the more Brownian motion there is, the more it will cause fluctuations, and so your mean square displacement value will rise. So greater temperature means greater Brownian motion. This you can also think of it like, because greater temperature gives you more thermal energy to the particles that are present in the some molecules in the suspending medium, so that will have more energy to cause an impact on the colloidal particle that is present in that, so that in turn will cause you more Brownian motion. You can think of it like this. And viscosity, how it is defined, basically you can directly see there is an inverse proportionality relation. So the more viscous the liquid medium is, the more viscosity it has, so the eta value will be greater, and then delta x square will be smaller. That means Brownian motion will be less prominent, because this is simple, because one is this mathematical relation directly telling you there is an inversely proportionality relation, and the other is that viscosity is some kind of liquid resistance you can think of. So the more resistance the liquid will give, so the colloidal particle to move in a random zigzag motion, the tendency will be decreasing. So because of which higher viscosity will give you less prominent Brownian motion. Then size. So size means a colloidal particle's radius, you can say. So here there is also inverse proportionality. That means I was also telling it earlier that the larger will be the size of the particles that are suspended in you, the lesser will be the possibility to see Brownian motion, because you can only see prominently the Brownian motion on very small sized particles. So you can choose from the option, that in which case the answer is only A, because greater Brownian motion is only seen from higher temperature but lower viscosity, so this is wrong, and lower size of particles, so this is also wrong, and all of the above is also wrong. So the option is A. Now question number 8. It is saying that in Perrin's work, which is basically the experimental proof for the first time of that was done in support of the Einstein's theory of Brownian motion. So in Perrin's work, in order to study Brownian particles, there are 4 options given. So this question is about how Perrin's experimental work was taken into actually was done. So this is very interesting, because at that point of time, when many of the facilities are not so much improved as improved we have science right now, but still he could measure, and he could identify that Brownian motion is observed, and he could actually quantitatively calculate the value of the Avogadro's number directly using the formula given by Einstein. So basically it proved the theory correct. So this question is about that experimental part, that to study Brownian particles, what was the configuration that he used. So there are 4 options. Option number A is that the photograph of the particle movements are captured periodically, that means after a certain interval times, and in terms of capturing the photographs. So this is option number 1. Second option is that the real-time particle trajectories were drawn by hand. No time, like there is no specification other is given. Now the third option is that, which is our correct option in this case. I'll tell you why. Because it is saying that the particle positions are drawn manually by hand at a given time interval. Means after a certain time interval of 30 seconds or 50 seconds, whatever, the particle, that position of that moment was drawn manually by hand and thus measured. And the third and last option is that the particle numbers are calculated from captured photographs. So you can see option number A and D tells you that Perrin took photographs, and from photographs he captured the movements or the position of the particles. And option B and C are focusing on that he manually, by hand drawing, he took the trajectory and the current position of the particles, and not by capturing photographs. But the only difference between option number B and C is that in C it is particularly mentioned that the drawing is taken after a certain time interval, which is not explicitly mentioned in B. So basically, to actually explain this thing, I had these all earlier pictures just for a simple understanding, that this is pictures taken from the internet, of course, to actually give you an idea, because I found it very fascinating. So Perrin used at that time he used a strong, obviously a powerful microscope is first needed to actually capture that the particles are moving, the small particles in the suspension. And fitted to the microscope he had this particular instrument called, I think it is called, I am not sure about the pronunciation if I am making it right or not, but something called camera lucida, I think. So this is an instrument that in the picture this person is using. So this is an instrument where you are looking into an eyepiece over here, which has a prism fit into that in such a particular angle that this is the object that he is trying to draw a picture of, and this is the paper on which he is drawing. So basically he is not directly looking at this picture, but he is not looking and then drawing. Rather than doing that, he is looking through this instrument called this camera lucida, which is basically arranged in such a manner that light is coming from the object, it is getting reflected into the prism inside this part in such a manner that ultimately it is causing a image of that same object superposing on top of the paper. So it is basically as if he is stressing out on that image that he is seeing through it. Okay, so the real life of picture, if you see, this is a YouTube video on from which I have taken the screenshots. You can directly watch the video. There are plenty of videos, as I said. So this is the instrument, let's say. This is the eyepiece from which you will see to draw the picture, and this is the scenery which we want to draw the picture of. Now what this has been used earlier many times by artists, and especially in science, when you need to draw very accurate diagrams but in a very easy manner. So you can simply look through this thing, and you will see that the inside there is a prism which causes the reflection in such a way that this image that you are seeing in front of you, this scenery, is basically reflecting and you are seeing it on the paper that you have put below for you to draw, and you are just outlining your uh, hand drawing it by outlining on that image superposition that you are seeing on that picture. So this is what exactly Perrin used for his experiment. That this is the configuration, that this is, let's say, the prism that is set inside this instrument, and you are looking from top. Your eye is set on that prism, this eyepiece here, and your object that you are going to draw or you are going to capture is, let's say, this is the object. Now light is coming from that object, and this is, let's say, see, the prism has a particular shape like that. So the light is coming, it getting reflected from the 45-degree walls of that prism, and ultimately when it is coming out and reaching your eye, so you are seeing that this is exactly parallel to the light trajectory that is coming from the paper that is present below your lens to draw the picture on. So basically that is how your object is here, but you are seeing a direct image of that object on that paper that is present below. So on that image you can directly hand trace the total picture, and you can get a very accurate outlining of that picture. So like, say here this person is using this. Okay, so this, here there is a prism, you can see that there are this glass thing, and this object is exactly, so from here light is coming and reflecting inside in such a configuration that ultimately it is causing an, so you cannot see here but this person is seeing it. So he's seeing the image here and he's just hand tracing the whole thing. So this is a very interesting thing about this experiment that was done very simply at that time, that Perrin was basically looking through the microscope and he was seeing the Brownian motion moving colloidal particles, and he used this particular arrangement to hand draw the particles. This is the reference diagram of how the this hand drawn thing was done. This was a graph paper he took. On that graph paper he followed a particular colloidal particle, and he actually hand drawn the trajectory of the particle after every 30 seconds in his experiment. Okay, so his time was 30 seconds. So he was following one particular particle, and let's say he started here for a same for initial time, and then after 30 seconds he saw that it has moved to here, so he has he has marked the coordinate of the particle at that time here, and like that on the graph paper for a significantly long time he took on the observations, continued with the observations, and finally he got the delta x1, delta x2, all these values. Just he has to do the how much is the displacement on the graph paper, basically from this hand trace diagram. And this happened in real time, like, I mean simultaneous. The advantage of this setup is that you can simultaneously see the thing, that is the image, and you can simultaneously at the present time look at the trajectory by simply hand drawing it. So this was at present time when people do such experiments, they do not do the hand tracing thing anymore because that is too much tedious to do. In modern time there can be images captured, and from analysis of that images data you can see the real time, you can program it like that, you can see the real time trajectory like that. So that is, but at that point of time that image capturing thing was not so much developed, so Perrin used to real time hand draw it from using this kind of an arrangement, and it has to be noted in a particular interval of time every time. So that is what it should be maintained uniformly, so you cannot, otherwise the observation is not statistically correct. So basically that is my argument for this answer that I have chosen, that the particle positions were drawn by hand at a given time interval which is fixed all the time, and I think for his work he used 30 seconds. Okay, so that is our right answer is C. Then equation number 9 is that the ratio of Avogadro's number as measured by Perrin, which is marked as Na Perrin, and modern day accepted value of Avogadro number, which is Na modern, is R, and you have to tell what is the value of R. First of all, I have seen two different values of Na Perrin from two parts. I am not sure which one is more accurate, I did not verify it, but whatever value we choose, the right answer will always be greater than 1, not equal to 1, not less than 1, and not even slightly less than, much more less than 1. The real answer is obviously Na Perrin is greater than the Na accurate. He slightly overestimated it from his experiment, because from the modern day accurate Avogadro's number, we know that the number is 6.023 into 10 to the power 23. But as far as I have obtained the information, is that Perrin got the value of something as, I think, let me check what was the value. Yeah, so at one position I saw this is 7.15 10 to the power 23 per mole. All of these things are per mole, obviously. And another part I saw the value as 6.82 into 10 to the power 23. So I am not sure which one is correct. I did not verify it. But whatever the case is, you can see that both are greater from the modern day accepted value. And so basically the ratio will be slightly greater than 1 if you choose the ratio in a Perrin by in a modern. This is greater than 1. But you can see how much accuracy, how much close to the accurate value he got to. This is like really mind-blowing that he by using that simple experiment he was able to get such accurate values to the exact value. Okay, so then our question number 9 is done, and the last question we are left with is again a mathematical problem. So it is saying that a gas of molecular weight capital M is kept in a column of height h and a temperature T. So the pressure and number density at the base level Z0 is P0 and N0 respectively. Then at what height the number density falls off at 1 as 1 by E. So again from the question itself you have probably understood that you have to use the formula of this equation of N equal to N0, this whole thing, or in also terms of P, because pressure is also given. You can whatever is sufficient suitable, but you have to use that part. So let us do that, and we'll be done with the assignment of this week. So question number 10 is basically saying that let us draw a diagram for our reference. So this is your base level, okay, and this is at Z0 height, and the vertical height of another level or layer you can say, which has a thickness of dz. This is sitting from the base level at a height of z. So this is z, and this is the considering the thickness, this is z plus dz. Temperature is uniform here T. The mass, obviously the molar mass is capital M given in the question. The pressure on this level is P, and the number density per volume is N. And the pressure at the base level we see, so take it P0, and the number density on the base level we take it as N0. Okay, so these are all standard, so we will directly go to the standard formula, which is N equal to N0 e to the power of minus mg z minus z0 by RT. Okay, so then here in the question it is asked to you that when the number density falls off to 1 by E times the base level value, that means N becomes N0 by E, that is equal to N0 e to the power minus mg z minus z0 by RT. So this N0 and N0 cancels out, so you get e to the power minus mg z minus z0 by RT equal to simply 1 by E means e to the power minus 1. So this minus and this minus cancels out, so it gives you mg z minus z0 by RT is just 1. So from here you get your z minus z0 equal to RT by mg. So you get your z value as z0 plus RT by mg. So thus you have calculated what is the height from base level of the level that you want to see where the number density has fallen off 1 by E times the base level's number density. So this is the value of Z that we were asked to answer, and this is option number A that will match to your options. So yeah, so option number A is the correct answer. So I think we are done with this week's assignments. I hope it has been understood by you. If there is any doubt regarding any of the questions, feel free to ask now, and if not, then I will probably end today's session.
Didi?
Yeah.
I want to know that if I have any query in assignment question, can I ask here?
Regarding current week's assignment, or like what means?
Current week.
Yeah, you can ask here. But just remember, because we are not instructed to solve the actual assignment for you, sometimes the questions match with the current assignment, but we are not supposed to solve that current assignment before the actual deadline that is given to you. So I can give you hints or discuss with you how it can be solved, because mostly the problems that are given in current assignment are of the similar pattern that I solve with you in these tutorials. And sometimes, like
Yes.
in this week's case, I think most of the problems are exactly matching with the actual assignment. So just keep that in mind, otherwise we can discuss. um,
Okay, okay. In a question, so that involving the suspended galvanometer mirror experiment. So the theory I can't understand here.
Suspended galvanometer experiment, it is it a question in the current week's assignment?
Yes.
In this like Brownian motion, okay, so I probably did miss that question. So what is the question, like, if
The question is that actually the theta square average is given, torsion constant is given, temperature is given. We have to calculate the Boltzmann constant.
calculate the
Boltzmann constant KB.
Boltzmann constant. Okay, so we are not sure how that is to be done. Like, do you get what
Yes.
is, like, as I always say, you have to first know what are the known parameters to you, and then what is the thing that you are supposed to calculate out of that. So once you are
Yes.
clear about that, you can directly find a connecting formula that connects the unknown parameters with the known parameter. So have you found what can be the connecting formula in this problem?
No, actually the theory I can't understand
Okay, so
involving the.
basically here, because it is a tutorial session, so most of the times I will not be going to too much detail of the theory discussion, because that is already in the lecture.
Yes, yes.
Sometimes I may cover it, but like say today we don't have much time enough, but I'll tell you what is the thing, that formula that you need to use over here. So you have to use that concept of rotational Brownian motion, where instead of this, like say delta x square average, this formula that you are using multiple times, the Einstein's formula, right? So like this formula that we have written down over here, yeah, this formula. So this is, let's say this is for a linear kind of a motion, where this is a linear motion along
Yes.
x direction. But what if, because Brownian motion is not just a translational motion, right? Because it is a zigzag kind of motion, it can be rotational motion also.
Yes.
So in case of rotation, instead of this x or a linear displacement, you have a angular position given to you, I think. So that angular position sometimes in the problem is given as theta, and instead of then delta x squared, you can be given terms as delta theta square average, or sometimes theta square average, whatever terminology they are using in the problem. Okay, but the whole concept remains just the same. I think there is some quantities that may differ, but there is a particular formula for that, as far as I remember. Let me just check. So I think there is a formula as alpha square average, as I can see, is RT by NA into 1 by 4 pi eta RQ into tau. This is a formula, you can look it up into the topic called rotational Brownian motion, where instead of considering translation motion along x direction, you choose angular position and take it as alpha, and then take the mean square deviation of that angular position. But the parameters you need to know are exactly the same. Like here also you have this viscosity eta, you have the particle size radius r, and the interval time tau. So I think the problem you just mentioned, that has parameters connecting to that, right? So you mentioned something about theta, right?
Yes. Yes.
So do you now get it? Like, can you use this formula and solve that?
Yes. 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 Yes.
Yeah.
Yes.
So,
Thank you.
and as per the idea behind this, you just look it up into Google or any internet source, or maybe the lecture videos or any book, on a good book or thermal physics. So you can look it up under the rotational Brownian motion, and probably it will be clear to you. But the
Yes.
whole
Yes.
idea is just the same. Just instead of translation
Yes.
motion, you are choosing rotational motion and angular positions. All
Yes,
right.
ma'am.
Okay.
Yes, ma'am. Thank you.
Okay. So let us then finish this class and we will meet in the next class.